Okay, our next speaker, professor here at Stanford University, Biondo Biondi, and he's a professor of geophysics and also a GSEP principal investigator on the exploratory project Electrochemical Dinitrogen Fixation. He graduated from Politecnico di Milano in 1984 and received a master's degree in 1988 and a PhD in 1990 in geophysics from Stanford. He's also the director of the Stanford Exploration Project, which is an academic consortium with a mission to develop innovative seismic imaging methodologies and educate the next generation of leaders in applied seismology. He is also the co-director of the Stanford Center for Computational Earth and Environmental Science, which leads the School of Earth Sciences computational-oriented research and educational programs. In 2004, the Society of Exploration Geophysicists honored him with the Reginald Fessenden Award. And in 2006, Biondi published the book 3D Seismic Imaging. That was the first book to introduce the theory of seismic imaging from the 3D perspective.
And good afternoon to everybody. And I would like to start with thanking and acknowledging the work of my two students that are listed there. Short Derrida, he is the senior one and is ready to defend his thesis. And I'm glad to say that I have instead a junior one, that is Jason Chang, that is going to pick up where Short will leave off. And I should also say that in this case, the students not only provided the real work and the sweat, but also ideas and creativity. So I'm glad to acknowledge them. Of course, we are going to have a change of scale. We go from the molecular scale to the field scale. My talk starts from the premises that indeed you know how to separate CO2 from other combustion gases, and you know how to pump it out in an economical way, and that you have reasonable confidence that the CO2 will be actually stay down there for ages and will not come up at the surface. However, things go wrong sometimes in life, and the Earth is heterogeneous. We Earth scientists repeat that among ourselves very often. And more heterogeneous than we like to think, and always surprises us. So I think that is clearly part of the CO2 sequestration project should be a monitoring to make sure that we understand where the CO2 is, and hopefully it stays down there in the reservoir that we are planning for. And in the unlucky case in which instead wants to escape and come up to the surface, that we have enough warning to avoid life hazards or other problem from CO2 suddenly coming up at the surface. Now, this is an image downloaded from the web. You can find many of them similar to that, and basically represents many different ways of monitoring a CO2 sequestration project. I will describe them as a two kind. One that they localized, intensive, accurate, and probably also cost efficient, because it's just a matter to have some sophisticated equipment downhole mostly, but even at the surface. And then there is the volumetric ones. Because the Earth is heterogeneous, really measuring things at the wellhead or down the well is not sufficient to assure that the CO2 stays where we want. We want to measure the CO2 where it is far away from the wells. And for that, probably only geophysical remote sensing techniques can help. Now, there are many geophysical remote sensing techniques that can be used for the application. I will show you some synthetic aperture radar from satellite data as an example, gravity, some electromagnetic. But in the oil and gas industry, the prime remote sensing technique to image volumes is seismic. And that is not by chance. It's because it has the penetration, the resolution that allows us to image large volume of data. And so an obvious choice for monitoring will be to have an active 3D seismic data in which we do have sources at the surface. Sound waves go down, are reflected up, and they're recorded up at the surface, and we can create an image of the subsurface. And that works well, and works well for CO2 sequestration as well. It has just a little challenge that is expensive. The good news is that the recording site of this part is actually getting cheaper and cheaper, and we'll discuss it briefly afterwards. The one that is unlikely to become really following any exponential curve in going down in price is the source site. Generating sound waves isn't expensive. It's interacting with the physical world. It's not just a virtual world kind of operation. And as such, is quite expensive. And if you think that you want to do that every 6 months, every year, depends on the really time scale that you think that you need to, and you have to do that for centuries, then I guess the budget gets big pretty quickly. What I'm going to talk about is actually getting rid of the sources and just having the receivers. And many of them at the surface. We are talking many. We are talking about 1,000, 10,000, probably soon millions of receivers that you can deploy at the surface in a cost-effective manner. Good news also to have a receiver there that if you need, if passive monitoring tells you that you actually something is happening, you can go back then with your sources, with your expensive sources, and get even more accurate images of the subsurface that you can get with the passive monitoring. Now, I'm going to tell you the application of a technique that is called interferometric seismic imaging. This technique actually has been around for quite a bit, originated here at Stanford. Jean-Claude Baut, one of my senior colleagues, invented it in '68. And that graph is a naive one that you could do by hand in '68, is out of John's original publication. And so it was invented on Earth, but interesting enough, the first time that was used in any reasonable scale and being useful was up in the sun. The helioseismologists, and here at Stanford and NASA in particular, they put up a satellite for recording Doppler data from the sun. And that you can think about, they were recording continuously passive seismic data from the surface of the sun. And using the idea of interferometry, actually they learn a lot about the sun. A lot of what we know inside of the sun, actually we know now by helioseismology. And this image here is just an image of the velocity structure under a sunspot. And we see some low velocities there. And the techniques is not very different from what I'm going to show you, the results that actually of velocity structure in the subsurface I'm going to show you later in my talk. Now, from the sun, it came back to Earth. Shame on us, exploration seismologists. The first one actually that made it to work were the earthquake seismologists. This is from a paper actually in Nature, not in geophysics, that was published in 2005 and give you the velocity structure in South California. And a lot of what actually makes the technology possible, as we'll see, is an improvement in receiving technology. But before that, we look at the results. Let me describe to you the concept of the method of seismic interferometry. Those two triangles are two receivers, in this case, in a volume. And those arrows means basically seismic waves going back and forth. That is what we call ambient seismic noise. And this is the energy that we are going to leverage. So no need to injecting seismic energy in the subsurface. We are going to use what naturally is there. Now, in reality, we are not measuring in a volume, but in a half space. We do actually have a surface, and we place the receiver as the surface. And actually, the surface plays a quite important role in what I'm going to talk about. So we start from the ambient seismic noise. Now, what is maybe not obvious, and actually when I hope that when I show you the movies is quite surprising, is from this incoherent noise, we can actually synthesize coherent waveforms and coherent data that in many ways are equivalent to the data that we'll be recording if we had an active source at the surface. The basic idea is the one of cross correlation. And what I'm going to show you is just using pictures but there have been quite a bit of sophisticated mathematicians that actually demonstrate that with quite rigorous mathematics, but I'm not going to bore you with that. And just so you show you the pictures, the idea is that we have one of these waves moving left to right. First is going to hit the red receivers and then the blue receivers. And if we correlate the two receivers, we're basically synthesizing with the data that we'll be recording if we had the source at the red triangle and the receiver at the blue triangle. If that wave is traveling at the surface or at the interface, maybe the interface between the ocean bottom and the ocean itself, so it will be either surface waves or interface waves, what we measure is the seismic waves as if we had a source at the leftmost receiver. That is for surface waves. There is another important set of waves traveling in the Earth that we call them body waves that actually generate a reflection. And this is the kind of path that of such reflected body waves from the subsurface. And the surface here plays the important role of sending it back in the subsurface after it hits one of the receivers. And again, we want to synthesize the equivalent of an active reflection. Now, this is for the concept. This is going to be applying the concept. On the left panel, I have a movie of this seismic noise recorded from 2,500 receivers at the ocean bottom in the Norwegian Sea over an oil and gas reservoir. And this is going twice the speed of the real speed. And on the right is basically a vertical section along one of those cables as a function of the distance, horizontal and vertical, the time. Now, taking that uncorrelated seismic noise, still on the left, that is the result of, on the right now, is the movie of correlating all the traces with one trace placed in the middle of the array, and where now you see the seismic wave starting to start. So this looks like so much a seismic wave that was generated by an artificial source. But this is just based by created by cross-correlating the noise on the left. Now, we can do that for every location in the array, and then we will record basically a data set that is equivalent in many sense to the one of an active data, and we exploration seismologists, we know how to deal with that, and we'll describe what to do briefly afterwards. So now we have a method. Let's ask some of the questions that we wanted to answer with this GCEP project. I should say that I'm reporting on the results of what is called an exploratory project. So it lasted 1 year and mostly supported one of my students. And we had a few research questions to answer. And we'll see that for some of them we have answers, some of them we don't. And that we may need further work. Can we monitor a CO2 reservoir by reflections? And that will be ideal because we know that actually we can. This is the probably best known example is example of monitoring the Sleipner CO2 sequestration, which is a fairly large scale sequestration, is 1 megaton of CO2 a year in the North Sea. And this is CO2 that was co-produced with natural gas and we injected down in saline aquifers. It started in '96, and there were at least 4 seismic surveys, active seismic surveys, were recorded on the top of this sequestration project. The images on the top are vertical sections. The images on the bottom are horizontal sections. And what we see clearly going from no sequestration to sequestration, an increase in signature. That's because it is well known and documented and studied that by injecting CO2 in the subsurface, you decrease substantially the seismic velocity. But decrease the seismic velocity will basically create reflector in the subsurface, and that's what we are seeing the signature there. So we know that by reflection, we can monitor very well, have a very good, precise, even quantitative. There have been done work, like the one cited on the slide, that actually connected quantitatively the amount of CO2 injected with seismic signature. Now, If we cannot create sufficiently good reflections by passive data, can we actually, using the surface waves the virtual surface waves to monitor the CO2 in any useful way? A direct way will be if indeed we do have a plume that is coming towards the surface, and we would like to know that it actually is happening before that it comes up at the surface. So maybe we are not able to image down kilometers, but we may be able to image a few hundred meters and get an early warning, maybe an early warning that motivates us to have an active seismic survey instead of just of a passive one. So can we actually detect the signature of CO2 that is lowering the seismic velocity using passive data for plumes coming up at the surface? That is still a direct detection. Even more intriguing will be an indirect detection, in which actually we do have that the plume coming up towards the surface, it does work as a pressure conduit in the subsurface, and changes the stresses close to the surface, way before that it gets close to the surface. So maybe even when it's still down kilometers down in the subsurface, and we can see that something is happening, something in the changing in the subsurface that maybe warrant, again, an active data set by looking at the effect of a change of stresses in the near surface on the passive data. Now, this idea of being a pressure conduit and seeing the effect of CO2 pumped down in the subsurface at the surface, it still has been proven in practice. This is a good example of a CO2 sequestration project, again, large scale in the Algerian desert, run by BP and Sonatrach, and in Salah. And the blue, the wells labeled in blue there are CO2 injections. And I'm not going to describe in details all the pictures here, but the important one is the one that appeared on the screen now that is relevant to that little patch here close to two of the injectors. And what we are seeing there is the deformation at the surface that was measured by synthetic aperture radar from satellite flying over the site. So even if the CO2 is still believed to be kilometers down in the subsurface, we actually observed a change at the surface in terms of an elastic response. But elastic response also bring in changes in stresses. Can we measure that seismically and not only with synthetic aperture data? Now, one thing that is making somewhat a lucky is somewhat serendipity is a good coincidence in time between the desire of monitoring CCS project. There is something that is happening in the seismic industry that is basically coming at the right time, and is basically the availability of cheap sensors. This is a log-log scale, represents what I would call the Moore's law for seismic acquisition. Is something that in the active seismic community is quite important, is basically the number of channels that you can use with a reasonable money investment kind of routinely as a function of the years for one single source. So this is one active source, how many channels you can deploy. And it does follow an exponential curve with doubling every 3.5 years. It's not as fast as Moore's law, because there are a few pesky real-world issues with actually recording seismic data, but nonetheless, it goes up exponentially. And we are now in the hundreds of thousands. We can expect by the end of the decades to be in the millions. And when you begin to record millions of traces, then you can do a lot of things with your even noisy seismic data. And the good news is that also this, if you want, technology advancement, is having an effect on the way the data are acquired for oil and gas, and gave us at least 3 data set in which we can test out our ideas on the cheap, in the sense that going and acquire this data will be terribly expensive, but oil and gas company now they're doing it. for the purpose of monitoring an oil and gas reservoir, not for CO2 sequestration, but we are piggybacking on them, and so we test out our ideas on using that data. This is one of the first one that I'm going to use the most is from Valhall, is a field in Norway. In many ways is one of this life of field seismic arrays, is the granddad, was one of the first one. It has 2,500 groups, 4C. When you say 4C, means there's 4 components. There is a pressure sensor that is an hydrophone in case that you are at the bottom of the sea, and accelerometers along the 3 Cartesian direction depth and the 2 horizontal ones. Good news also that was not obvious is that all these instruments, they are really built to record the higher frequency data, but they are good signal to noise at the low frequency, the kind of frequency where actually you do have useful natural seismic noise. There are 2 data sets that I'm going to show you some results and we are going to work on. One is in Long Beach in South California. You see on the left, there is a large oil field. There is a company that has been recording data on that field with semi-permanent sensors using MEM sensors, and in this case deploy 3,000 of them. And every little blue dot on that slide represents one of those sensors in people's yards, in parks, and on the road. And the other data that we are going to use is similar to Valhall, was in Ekofisk, that is another oil field in the North Sea. But in this case, the data were recording using fiber optics. So why is it important? Because fiber optics is likely to be the instrument of choice. They are more cost effective, don't need as much power to operate. And so being able to actually get good information for fiber optic sensor is important. I'm not going to show you the result from here, but just yesterday the student showed me on my screen that indeed you can get very nice virtual sources from the Ekofisk data, but it's way too fresh. Here, just a point in terms of the data size. This kind of arrays, the one Long Beach records 0.5 terabytes a day. The Ekofisk is almost 3 terabytes a day. I was at lunch with a gentleman from Slack, and running those big accelerators, they do record tons of data. I think that in seismology we are getting there, and that will be a system engineering problem in terms how much you want to record on site, how much you want to pre-process on site, how much you want to store off site. So that will be interesting system engineering if you deploy this in the real world. This is a spectrum as a function of time for Valhall, and it basically shows that a reliable seismic ambient seismic field we can really measure in the low frequency between 0.5 hertz and 2 hertz. We hope to get higher frequency, but that is what so far we have. And higher frequency, hopefully the signal to noise will come up as we correlate more data with more receivers and for longer time. On the left is a time slice from a movie that I showed you before. On the right is, again, a time and distance to give you a sense of those arrivals. And what we are going to use are really this interface of surface waves. And you see that the arrival time is a function of the frequency. This dispersion of arrival time as a function of frequency is what will actually allows us to have not only lateral resolution, but vertical resolution. We would like to see reflections. Unfortunately, at these frequencies, the reflections are really lost here together with the first arrival of the surface waves. A reflection we should start to see at a few seconds, and you see that wavelength is pretty long. So we really need to see reflection, we need a higher frequency. And so we are not really seeing a reflection. So the first question is, can we use reflections? That will be ideal. I would say not yet. I'm not given up on it yet, but clearly is not what I'm going to show you today. The second question is, can detect directly the effect of CO2 plumes before they reach the surface? And I will say yes. And this is next couple of slides are the most important of my talk, because I think they are the most impressive results. Now, the panel on your right shows a velocity map that was derived using active seismic data. On this array, the companies go every 6 months and shoot active seismic data. They used the most expensive and computation-intensive process that is called full waveform inversion to get the velocity map on the right from the active data. The map on the left is the velocity map that we got from basically applying tomography to the arrival times of coming from the slide that I showed you before, the arrival times basically of these waves. And of course, it's not as nice and high resolution as the active data, but the imprint of those shallow channels around 100 meters is quite clear. And the good news that all these maps that we are getting, they're actually repeatable. I am not showing them here for the sake of time, but if you just measure this map one day and then after a week, you can actually repeat and get similar results. That means that is indeed geology, is not artifacts or noise. This is at 100 meters down. This is at around 200 meters down. Now we have a low velocity anomaly, as potentially will be a CO2 anomaly that is visible on the passive image and is also visible on the active image. Together with the high velocity, it is the red channel. The red channel, we only see the edges. The active data image outside of the array, because the sources are going to be outside of the array, so we are going to illuminate what is outside of the array with active data. With the passive data, we are only stuck with creating our virtual sources that correspond to the position of the receivers, so we just image within the array. So indeed, I think that I'm comfortable that we will be able to detect low velocity anomalies in the near surface of at least a few hundred meters if CO2 is coming towards the surface. Now, the other interesting question is, can we detect before, when actually is an elastic and a stress effect is not a direct effect? We have not done that from the passive data, but the good news is that the two of the data sets, the one from Valhalla and Ekofisk, those are two reservoirs that are chalk reservoirs, and over the years, producing down in the chalk, taking out the oil, pumping water, actually has created a substantial amount of subsidence. In Valhalla, about 6 meters, in Ekofisk, even more. And the subsidence has changed the stress field close to the surface, and it's created what we call velocity anisotropy. So basically means that now the velocity is not only change of the location, but also depends on the propagation direction. Good news that having an array that illuminates the subsurface from all that direction, we should be able to measure that anisotropy. We have not done yet from the passive, has been done extensively from the active data. This is just a picture from many publications that have analyzed anisotropy from Valhalla, same things from Ekofisk. So we have not done it yet. We will run the test on Valhalla and Ekofisk data, and we will be reporting shortly. Last example that I'm going to show you is from Long Beach. Most of the sequestration projects that we'll be running are likely to be on land, not on the ocean. Can we actually get information out of noisy land data instead of quiet marine data? And here is your noisy data. We are in Los Angeles. As you may guess, many cars goes around in Los Angeles. And you see the movie on the right is just the data recorded in the Long Beach array. And you can clearly see Interstate 405, big noisy strip here, corresponds, if you look at the map, there is Highway 1. So this is during rush hour, and we do actually have a lot of noise. Question is, notwithstanding this noise, can we actually synthesize good passive data? Here is, we are seeing it on the left, and that is pretty fresh results as well, coming only a few days ago. And we indeed, only 12 hours of correlation, so we could do much longer than 12 hours. Time scale of what we want to monitor is much longer than 12 hours. We actually get very reasonable virtual sources propagating through the Los Angeles basin. So indeed, I think that we will be able to monitor CO2 sequestration on land as well. Now I'm close to run over time, so what is coming next? We would like to analyze the Long Beach data for time lapse. We actually have available 3 months of data, so we will look at data acquired from far apart to see if we see significant differences. We will analyze Ecofisk and Valhall for anisotropy, so to see if changes in stress field can be actually used to detect interesting things that are happening in the subsurface. And we're going to look in both 3 data sets to maybe actually bring up the signal to noise at a high frequency and to see not only just surface waves, but also reflections. And then finally, ideally, and one of the things that prompted me to be here, we would like to record data on an actual CCS project. So if any of you got interested enough in my presentation to be interested to do that, I would appreciate if you contact me by email or even today. And then finally, I would like to acknowledge the GSEP for the financial support and the ACP affiliates for the financial support as well. ExxonMobil and Schlumberger, they're actually there is an intersection there. They're both supporting there. And people and companies that have given the data, BP for the Valhall data, Signal Petroleum for the Long Beach data, and ConocoPhillips for the Ecofisk data. And thanks for your attention, and I will be happy to answer any question.
Yeah, that would be really great if that could actually work. It looks exciting. So how long is it from this very early analysis that you've done till we might actually be able to go? For example, there's the Gorgon project that's coming along in Australia. Would it be possible in the next couple of years to implement these kind of monitoring systems, or will it take a lot longer before it's really ready?
I do think that the further analysis that is summarized in the slide that I had up there will confirm that we can do some interesting monitoring. Now, how deep we go, I think that one important question is, can be used only as an early warning of a plume coming up, or is actually can be used to hopefully there is no plume, and to understand how it evolves the CO2 in the reservoir as is injected down at depth. And that is really, we need to have reflections, because with surface waves, we don't go more than a few hundred meters down. There is also the potential of, as I said, the geomechanical effect that are longer distance. But that's, I think, that needs quite a bit of understanding of the geomechanics and the site to really trust that test. But I do hope that, yes, we will be able to convince Chevron and partners to have some monitoring in Gorgon in Australia. That's, I think, it is a realistic goal, and I've been talking with the people at Chevron for quite a bit about it.
So what about if you had microseismic events? Could those act as sources that you could use for imaging?
Oh, absolutely. I didn't mention that. There is another kind of seismic monitoring that is passive, is actually using, by injecting, you create little earthquakes, and first recording them and analyzing them, it just provides already useful information. Then using those microseismic data sources to actually image far away from the sources. That is the holy grail, not only of CCS sequestration, but of unconventional, and to use hydrofracking. So yes, that will be great. I'm definitely not going to stand up here and to say that it's easy to be done in a few years. I think that there are a lot of challenges coming with that. Thank you.